The first lesson in the Chemical Basics unit is on basic atomic structure. This lesson will be divided into two smaller videos. In this first video, we'll hit these first two learning targets. The first of which we want to be able to define and apply the terms atomic number, mass number, and isotope. So first of all, let's talk about subatomic particles. We know that atoms are made up of a nucleus. The nuclei of any atoms contains protons, which are positively charged, and neutrons, which are neutrally charged. The nucleus is less than 1% of an atom's volume. In other words, it's super tiny. It makes up hardly any of the size of the atom. However, it does account for over 99% of the atom's mass. The other part of an atom is the electron cloud. This is where we would find electrons, which are negatively charged. Most of the atom's volume is this electron cloud, which is actually empty space. The electrons simply move through that empty space. The electrons are much lighter than a proton or a neutron. This is why the nucleus, which contains protons and neutrons, is over 99% of the atom's mass, because the electrons are super tiny compared to the mass of a proton or a neutron. To put it in perspective, it would take roughly 1,700 electrons to equal the mass of just a single proton. So they are incredibly light compared to a proton or a neutron. Here is a depiction of an atom. Now note, this is not to scale by any means. Here we see the nucleus here in the middle, where we have the red particles with the plus signs for the protons. The blue would be the neutrons, and notice those are what make up the nucleus. And then we have the electrons moving outside the nucleus. Now again, this is not to scale by any means. The nucleus would in reality be much smaller for this size of an atom. And then also one thing to point out, electrons often are depicted as orbiting the nucleus in a ring, like you might think of here. That's actually not how they move. Actually, we know now that we don't know how electrons move in an atom. It's actually impossible to determine that. But oftentimes this is how you will see electron motion depicted in atoms, even though it's not in reality the case. Let's talk about atomic number. There was an English scientist by the name of Henry Moseley, and he lived in the years you can see here between 1887 and 1915. That's not something that you need to remember. Just put it on there for your reference. And what he recognized was that atoms of each element, they contain a unique positive charge. And this led to the discovery of atomic numbers, which we know now is the number of protons in the nucleus of an atom. What Moseley essentially discovered was that every element has a different number of protons, is what he was able to discover. So this atomic number, it is different for every element. If you go ahead and look at the periodic table that you have in front of you, you will see that every element does have its own unique atomic number. You'll notice that they're all whole numbers, and they are found on the periodic table. These atomic numbers define the element, and what we mean by that is kind of what we already said here. Each element has its own unique number of protons, meaning it has its own unique atomic number. So thus, if you give the atomic number of an element, you have identified what that element is, because no other element has that atomic number. So as an example, if we look at atomic number 6, if you look at your periodic table, you'll see atomic number 6 belongs to carbon, and that means that a carbon atom has 6 protons in the nucleus. There is no such thing as any other element having 6 protons. Likewise, there's no such thing as a carbon atom with anything but 6 protons. Another example, if you look at hydrogen, you will see it is atomic number 1, meaning it has 1 proton in the nucleus. Again, there's no such thing as an element other than hydrogen having 1 proton, and there's no such thing as a hydrogen atom having anything but 1 proton in its nucleus. If you find gold, you'll see that it has 79 protons, thus atomic number 79, and that would have to belong to gold. Here's a practice problem. Question: how many protons does a fluorine atom have? Well, find fluorine on your periodic table. You'll see it's atomic number 9, thus it has 9 protons. Which element has 26 protons in its nucleus? Find atomic number 26 on the periodic table, and you'll see that it belongs to iron. So the answer would in fact be iron. So we've defined atomic number. It is the number of protons in the nucleus of an atom. Note that if the atom is neutral, it is the same as the number of electrons, because that would mean that the protons have to be equal to the electrons. Because recall, protons are positive, electrons are negative, and so those particles have to cancel each other out. So if we have a neutral atom, the atomic number would also be the number of electrons. Alright, let's talk about isotopes and mass number. Atoms of the same element do not have to be identical. They very often could be, but they don't have to be. And the reason is the number of neutrons that are in their nuclei just might vary. So let's look at an example. Let's take potassium. If I find potassium in the periodic table, I will see that it is atomic number 19. So that tells me, assuming I have a neutral atom of potassium, it has to have 19 protons because it's potassium, and then it would have 19 electrons to go along with that in order to balance out the protons with the charge. However, there could be a varying number of neutrons. There are 3 different isotopes of potassium. One isotope contains 20 neutrons, another contains 21, and yet another contains 22. In other words, what we're saying here is isotopes, these are atoms of the same element with a different number of neutrons. There are a couple of ways that we can notate different isotopes of an element. We always identify isotopes by their mass number. The mass number for an atom is simply the number of protons plus the number of neutrons. Note that this would always make it a whole number, because protons have to be a whole number, as with the number of neutrons. Note that this number is not, I repeat, not on the periodic table. So when you look at the periodic table, you will not find a mass number for an isotope of an element, at least not most periodic tables. Here over the last couple of years, there have been some new periodic tables that have come out that's been a little more popular, I have noticed. However, the periodic tables that you will most commonly see do not have mass numbers on them. Okay? When you look at a periodic table, you see several different numbers. One of them is always the atomic number. The other common number you see on there is known as the atomic mass. That is not the same thing as mass number. That will be the primary topic of the next video. Note that the word mass number is not actually a mass, but it is close to a mass, and we'll discuss that idea a little bit later as far as what that means, why it's close to a mass. But when we give a mass number for an atom, it's not the actual mass of that atom. So let's look at an example dealing with this idea of mass number. So let's talk about a copper atom with 34 neutrons. So find copper on your periodic table, and you'll notice that copper has atomic number 29. So that tells us that there are 29 protons in a copper atom. So if I want to know the mass number for this atom, I'm going to take the 29 protons plus the 34 neutrons, and that will give me 63. So the mass number for this particular copper atom, the one that has 34 neutrons, is 63. Now, it is with this mass number of 63, that's how I will notate this particular isotope. And there are 2 ways I could do that. The first of which, I could just simply write out the element name, copper, put a dash, and then put the mass number, in this case 63, as we've calculated. The other way is to use the symbol for copper, and note that is the capital C lowercase u, and then we put the mass number as a superscript on the left-hand side, or preceding the symbol. So either of these, if you were reading these in text, you would read either of these as simply as copper 63. So you wouldn't vocalize the dash, you wouldn't say copper dash 63. Likewise, if it was in symbol form, you wouldn't say 63 Cu. You would just read them both as copper 63. So let's look at some more examples of this idea with mass number and isotopes. So first example here asks us to determine the mass number of each atom. Fluorine atom with 10 neutrons. So look at your periodic table, find fluorine, find its atomic number. You will see that it is 9. Recall that that tells you that it has 9 protons in the nucleus. So 9 protons plus 10 neutrons, that's 19. So its mass number is 19. Bromine atom with 44 neutrons. Again, find bromine on the periodic table. Find its atomic number. You'll see that it is atomic number 35. So 35 protons plus 44 neutrons. That gives you a mass number of 79. Now I'm asking you to determine the number of neutrons in each atom. So let's take a look at how this problem will read. So here I'm given sodium 23. And recall what this 23 tells us. That is the mass number of this particular sodium atom. So I know the mass number is 23. The fact that it's sodium, I can look that up in the periodic table and see that it's atomic number 11. Well, remember that means there's 11 protons. So if I want to find the number of neutrons, I will simply subtract the mass number 23 minus the number of protons 11. That will give me 12 neutrons in that isotope of sodium. Gold 197. Again, find gold on the periodic table. You'll see that its atomic number is 79. So that tells you it's 79 protons. So to find the number of neutrons, I will subtract the mass number, 197, minus the number of protons, 79. That will leave us with 118 neutrons. Alright, here's a practice problem. Like before, pause the video, try to do it yourself, and then play it and see if you got it right. Alright, first one here. Determine the mass number of each atom. Write a symbol appropriate for the atom. Alright, you've had a chance, now you've had a chance to do the problem, at least this first one here. Carbon atom with 8 neutrons. So if I look at the periodic table, I'll see carbon has an atomic number of 6. So that tells me it has 6 protons. So 6 protons plus 8 neutrons, so its mass number is 14. So the symbol would be carbon 14 as you see it here. Again, the 14 mass number goes as a superscript on the left side. Then we have the capital letter C as the symbol. So carbon 14 as you see there. Okay, try this one. Copper atom with 36 neutrons. You've had a chance to try it. Copper has 29 protons because it's atomic number 29, plus 36 neutrons. So 29 plus 36 is 65. And the symbol, we'd write as such with the symbol Cu, and the mass number there is a superscript on the left-hand side. And one more. An iodine atom with 73 neutrons. Iodine's atomic number is 53, so 53 protons, plus the 73 neutrons is 126. So its symbol, iodine 126, with the mass number there preceding the symbol as a superscript. Alright, here's another practice problem. This time you're doing the opposite. I ask you to determine the number of neutrons in each atom. So the first one here, we're given chlorine 37. So look at the periodic table. Find chlorine. You'll see its atomic number 17. So it has 17 protons. So 37 minus 17 leaves you with 20 neutrons. Next is boron 10. Find boron on the periodic table. You'll see its atomic number is 5. So 10 minus the 5 protons. That leaves you with 5 neutrons. Next we have vanadium 51. Find vanadium on the periodic table. You will see that it has 23 protons. So 51 minus the 23 protons is 28 neutrons. Alright, so here we have defined and applied the terms atomic number, mass number, and isotopes. Now the next learning target is really just an extension of this. It says determine the atomic number, mass number, and number of protons, neutrons, and electrons in an atom. So the best way to show you what this means is just to show you an example problem what this will look like. So notice here we have a table, and there are several columns in the table. We have the isotope, the symbol, the atomic number, mass number, protons, neutrons, and electrons. And for each of these, the atoms, it's partially filled in. So for example, for the first one here, we're given the atomic number, we're given the mass number. We need to be able to fill in the rest of these. We need to be able to indicate the number of protons, neutrons, and electrons, the symbol, and the isotope. So I'll do the first one here as an example for you, and then I'd like you to pause the video and see if you can fill in the rest on your own, and then play it and see if you got them right. Alright, so for the first one here, the first thing I see is its atomic number 28. So that tells me how many protons there are going to be, because I know the atomic number equals the number of protons. So there will be 28 protons in this atom. And assuming I have a neutral atom, and for now that's the only assumption that we will make, because we haven't worried about anything other than neutral atoms, that tells me that there's also going to be 28 electrons, because it has to balance the protons to make it neutral. So I know there will be 28 electrons. For neutrons, I know that the mass number has to be equal to the sum of the protons and the neutrons. So here I need to subtract. My mass number is 60 minus the 28 protons. That should leave me with 32 neutrons, and you see it there. Okay, lastly, I need to figure out what element we're dealing with. So for that, look at the atomic number. It's atomic number 28. Consult your periodic table. You will see that atomic number 28 is nickel. So I know it's nickel, but I can't just say nickel because that would not indicate the specific isotope. Recall we indicate isotopes using their mass number. So this would be nickel 60. Okay, notice the mass number here is 60, so the isotope is nickel 60. And then the symbol, I would just use the symbol for nickel, Ni, and the mass number goes there as a superscript preceding the symbol. All right, please pause the video, try these other three by yourself here, and then play it, see if you got it right. So you've had a chance to try these. So on the next one here, we're given protons and neutrons. Based on this information, what you can fill in, you know that there's 33 protons, so there has to be 33 electrons to balance that. And then the fact there's 33 protons means the atomic number is also 33. So those are the first things you can fill in. Next thing I would look at would be the mass number. I know that the mass number has to be the protons plus the neutrons. So 33 plus 40, that leaves you with 73 for the mass number. And then look at your periodic table to determine what element we're dealing with here. Atomic number 33 is arsenic. So this would be arsenic 73. Again, the mass number is used for the isotope notation. So arsenic 73, and the symbol you can see there is the capital A lowercase s. You can see the symbol written there. Alright, next we have silver 107, and looking at that I can fill in the symbol, just find silver in the periodic table. See it's Ag and then the 107 mass number. You'll see the atomic number of silver is 47, so you can fill that in. And the fact that the atomic number is 47 tells us that there are 47 protons. And again, assuming we have a neutral atom, that means 47 electrons. The next thing I would see is looking at our isotope notation, I see the number 107 there. Recall that is the mass number. So 107, we can fill in for the mass number. And then lastly, we're left with the number of neutrons. Recall that the neutrons we would get by subtracting the protons from the mass number. So 107 minus 47, that gives you 60 neutrons. And the last one here, we have uranium-232. So I'll just go ahead and fill in the isotope there. Again, looking at it on the periodic table, you will see that its atomic number is 92. So it has 92 protons and 92 electrons. And its mass number, we're already told, is 232 for this isotope. And so to get my neutrons, I simply need to subtract the protons from the mass number, and that would leave you with 140 neutrons. Alright, so in this video here we have defined and applied the terms atomic number, mass number, and isotope, and then you have now seen how we would go about determining those values, atomic numbers, mass numbers, protons, neutrons, and electrons, given some of that other information.